Swayam Prabha. Digital India. Educated India.
Today we will start with the section which is helicopter trim, or you say equilibrium. Okay. That is, if the helicopter is flying at a particular flight condition, what should be the control input? Okay. That is what is called the trimming of the helicopter. Now, for that, pilot input will be evaluated theoretically. How will you get the trim from what we have learnt till now? Because we have learnt inflow first, inflow, and then inflow was related to thrust. Okay, this is one equation, rotor inflow. Of course, thrust is the key. You have forward flight condition, attitude, everything is there. And the second one is flap response. For this, your input is pitch angle, blade pitch. Okay. And the third set which we obtained are actually the hub loads. Okay. Rotor hub loads. But the hub loads are in terms of flap, in terms of blade pitch and inflow. Everything is there in the hub loads. Now, if you want to trim the helicopter, that means you must know what are the all the external loads that act on the helicopter. You will have, in terms of loads, if you say it has several components. One is of course main rotor loads, main rotor, that means loads means all the 6 components, and then you have tail rotor, and third one is if you have any vertical fin. So, any vertical fin, that load, and then horizontal surface, these are all fixed. Then fuselage, fuselage aerodynamic load, fuselage loads, you can say fuselage means one is aerodynamics. So, you may say fuselage drag, because we normally get only drag. Okay, but if you want to do, you have to put a wind tunnel to take a particular point and evaluate the loads at different orientation, different Mach number. So, the fuselage loads is one, aerodynamic loads, and then the last one is the weight also, that is gravity. Okay. Now, what we obtained is only for main rotor hub loads. We have not, we do not have any of these things. Yeah. the shaft tail rotor can be mounted on a vertical fin. That means it is like a actual conventional aircraft, okay, and the fin can give its own load. Okay. So, that is why, but if fin is not there, then you neglect it. Horizontal surface, you will find this is a very, some helicopters have full big ones, some will have very small one, some may not have any horizontal surface. Okay. And of course, fuselage drag you have to do from wind tunnel. Then gravity acts at the CG. Now, once you have the loads, you have to transfer all the loads to the center of mass, but that means you must know the location of the center of mass for a particular configuration, means what the weight of that, how much fuel, how much everything. Okay. And then write the 6 equations of equilibrium, 3 force equations, 3 moment equations, but they will be in a particular coordinate system. Whether you want to write the equation in earth fixed coordinate or it is the body fixed coordinate, because you have to be very clear about that. All these loads, they are obtained in the body fixed coordinate system. So, it is always preferable to use body fixed coordinate system, transfer all these loads to that and then write the equations. Okay. So, you will have essentially 6 equations, force equations. Now, the helicopter, you know that it can be flying in, the hub loads were obtained when it is flying straight as a rotor, but the rotor can fly in any direction. That means the component of velocity you must take properly. Right now, what we will do in this is, because my fuselage may be like this, rotor may be, helicopter may be going in this direction, okay, lateral. So, you can have all velocity components, but what we have obtained is only one velocity. So, we will restrict ourselves to only forward flight, steady condition. And how this entire equations are solved? Now, the question is, what are my unknowns, what are my known quantities? That is very important. Before you really start off the entire sequence of this problem, you must know what are my unknowns and what are my known quantities. If you look at that, the known quantities, if you say, because let me put it, the unknowns, I will write unknowns, okay. Known we will worry about that later. Unknowns is theta naught, 1c, 1s and theta 0 tail rotor, then pitch, attitude, roll attitude. Okay. We normally use the symbol, okay, pitch and roll attitude of the helicopter. We do not know, these are the 6 quantities, and then of course, power. Okay. Sometimes you can do a particular case where power becomes the equation, okay, but usually that is not done. What you do is you calculate power after trimming the helicopter, evaluate the power, keep on evaluating. Okay. You may have power available. It is not that if you want to see what is my, I want to use all the power, what should be in my flight condition. Okay. That is a bit tricky. That is why best is you prescribe the flight condition and then you want this, calculate what is the power required. Now, when we prescribe the flight condition, first we take the very simplest case. Simplest case is, I will put it known quantities. Your mu, which is the advance ratio, this you say I know it, which is please note this alpha is attitude of the, basically alpha is that pitch attitude, pitch theta, okay. Alpha is that. We do not know this to start with, that is why you always use advance ratio I am using, okay. Assume that this quantity is known. Then weight, this is the weight of the helicopter. Of course, CG location must be known for the given weight. You can have forward CG, aft CG, etc. Then that F, which is the fuselage drag, related to fuselage drag, that F, that area, okay. Then of course, the rotation, then you need to know omega bar RF square, flap frequency. Then if you have the blade with a twist, you must know theta twist and theta. I will write what are this. This is the twist of the blade, twist, and theta Fp, which is the flight path, flight path angle, I will call it, okay. Later I will describe what. In addition to this, you have to know other geometric conditions. Where is the tail rotor? What is the distance from the CG? The tail rotor location. And then tail rotor dimension. If you want to take what we derived for main rotor expression completely, you can use it for tail rotor, absolutely no problem. Only thing is you have to use the dimensions, operating conditions only for tail rotor, okay. But tail rotor has only collective pitch, there is no cyclic. We have simplified our problem by considering only flap frequency, that is why I put what is the rotating flap frequency. And of course, if you want geometric, what is the precone, beta naught, then you must specify that also, geometric values, okay. Now, given these quantities, I will go and get those quantities and what is the power required for that particular flight condition. This is the basic question. We will draw one diagram and then I will describe. The diagram is okay. And you may have your CG somewhere here, this is weight, and the horizontal, this is your longitudinal, this is the horizon. Okay. In the sense the helicopter is flying in that direction, this angle is theta Fp, that is the flight path angle. With respect to horizon, that is all. Horizon is normally earthbound, it is a horizontal, okay. With respect to horizontal, what is my velocity vector? That is the flight path angle. If this can be 0 means you say level horizontal flight, okay. And this angle I call it as alpha. Okay. That is the angle, because this is what is required. This alpha comes here, because we cosine alpha in the hub. Now, you may say this is perpendicular to, if the shaft is perpendicular to the body fixed coordinate system, then it is fine, because this will be 90 degree, because you can have fuselage axis system and that will be same as hub axis system. Okay. On the other hand, if the hub is tilted a little bit with respect to the fuselage, okay, then you have to take that into account in the transformation. Usually sometimes it is tilted by 2 degrees, something like that. Okay, the shaft itself will not be perpendicular, that will be slightly kept. Okay. So, these are small details which one has to consider when you are writing the equilibrium equation. Now, given these quantities, and what is my pitch attitude? Pitch attitude is basically theta is alpha minus theta flight path, but I will use a minus sign because the rotations are counterclockwise, clockwise, positive, etc. Okay. This is the angle, pitch attitude of my helicopter. Now, this reference line, so I will fix 2 coordinate system. One is earth coordinate system, which you may have x, y and z. Okay. These are earth system, you may have x EA, EA. With respect to this, this is the body, capital X, capital Y and capital Z. You may call it B, B and B, that means body system. Okay. You have to get the transformation from this to this, that is by rotation, but you assume initially, because more complicated motions will take a little later. Right now we assume that the helicopter is only flying in the plane x, z earth axis system, but you may find it can fly in another direction. Okay. Then you may have to say what is the yaw also, because the heading can be something like this, because if it is making a maneuver, okay, that means the earth is a fixed coordinate system, but the helicopter heading can change, you follow. On the other hand, you can say my heading of the helicopter is same, but my velocity vector is this way, then you have a side slip, you follow, because you are also moving side. So, all these flight conditions, they become a little complicated, that part is a most general maneuver. That I will just describe, if time is there at the end of the class I will show that, otherwise, because that is a complicated thing, which of course we are developing it. Right now let us say this is the motion, the helicopter is flying only in the XZ plane, but the center of mass, I will draw one more diagram by the side, that is the view from rear. Okay. And weight, okay. So, there is a tilt about, because if you say with respect, this is my y body, z body, okay. And this angle with respect to this is my roll attitude, and this distance you may call this distance as y hub. Here you may say this is x hub and this is z hub. Then you can take to tail rotor, this can be x tail rotor, this is z tail rotor, okay. You can have all. That means essentially you have to locate every point. I have not taken any horizontal surface nor the fin, I neglected those things in my simple formulation. Okay. Now you know that because these are helicopter maneuvering anything, these rotations are not small angles, okay. So you have to follow Euler angle transformation, okay. The Euler angle transformation I will write between this, you find out the sequence of rotation. First you rotate about x axis, that means roll, and then after the rotation of x you rotate about y axis, okay. So that you get the body axis system, you understand. From the earth axis you want to go to body axis. So the transformation sequence, you first say roll, then pitch. So this sequence if you follow, it will be like this, okay. First is what is it, this is x, y, this is the body, but the rotations are counterclockwise positive I am taking, okay. That is why there will be a minus sign I have to introduce there. Multiplied by 1 0 0 0 cosine phi 0 x earth okay. This is the that means earth axis system, you first rotate about phi, you get the intermediate axis, then that intermediate you rotated about the pitch, and then you, but these theta are counterclockwise rotations, okay. So phi is a counterclockwise rotation positive. Then if you use that this theta, because this is here as per a diagram, okay, I have put a with the axis system clockwise rotation, okay. Theta I put it as alpha minus theta fp. So actually I must put a minus sign, yeah, that is fine, that is okay. You look at the, if you want I will describe it. See, this is y earth, z earth, okay. X earth is back, so you rotate about phi. So I call it x, sorry, y some intermediate prime, z prime, this angle is phi. So y earth to y prime, okay. cosine, minus sine, right. This is this matrix. If you put x1, y1, z1, you follow here x prime, y prime, z prime. Now you take here is x EA, y EA, right, 1 0 0 0. Here you will have cosine phi. The same thing it will give you minus sine phi, right. And here this is sine phi in the z EA, sine phi, cosine phi. Okay. This is fine. Now you got x1, y1, you got a x prime, y prime. Now you are in the prime system. You are giving a rotation about y prime. Okay. So you will have, this is my z prime and x prime is here. This is actually my y prime, x prime is coming out of the board. You are giving a rotation about y prime. Now what it will be? This is z prime, this is x prime. This is the z body, x body. Okay. Now you will see that it will get that. So do not just blindly, that is why in these transformations you follow them how they are given. Okay. Because now you see what is the transformation, because here you put x prime, y prime is 1, z prime, x prime cos theta and x prime sin theta. Okay. Whereas if you go to z prime cos theta, z prime, it will become minus sin theta. Okay. So that is why the minus sign there. Now with this you have the relation between earth to body. Why we have to use this is, because please note that I still do not know this and this angle, but I will not make any small angle approximation, because that is why please understand, the moment you have large angle they are not vectors. Okay. You have to follow this transformation. The weight is acts along the earth axis system. Okay. That is why you have to transfer the weight into body system, and then you can write all your equilibrium equations in the body system. That is the reason you need to have this transformation properly done. Okay. Now you got this, only thing is theta you have to put a minus sign, because as per the diagram, that is the key. Okay. No, please understand that there is a phi is rotated about earth axis. Okay. Whereas theta is not rotated about earth axis, theta is rotated about the rotated axis. Okay. It is not about the fixed axis system, you are doing the rotation. So every rotation is about the rotated axis, after you get a new position about which you rotate. Okay. This is the sequence you follow. Now if you want to, there is another transformation which is there, that is a, see, we have used all those things in our work. You rotate only about a fixed axis system, like what you said is, because you say should I rotate theta with respect to y prime?
No, I want to know
These are the Euler angles, that is all. If you have a heading, that also will come.
So these angles are basically with respect to Earth coordinate system.
Not exactly, these are Euler angles, do not say Earth coordinate system, because
Again, I wanted to ask you, what you get from the gyros?
gyro will give you rate, okay, that I will come to that later. Gyro will give you angular velocity. Angular velocity is a vector, because instantaneous angular velocity it will give you about 3 axis. If you have a 3 axis gyro, you will give rotation about the 3 axis. Now, the rate of change of attitude, please understand, there is a lot of difference between angular velocity vector of the body at an instant to rate of change of attitude of the body. There is a relationship. If the angles are small, you say angular velocity is same as the rate of change of angle. If not, see, because in the ALH you have to do one more, that is the kinematic relation, that I thought I will do it later if it is interest, if you need to know from flight dynamics point of view, because if you really want to solve that problem, it is, you have to know a little bit more. That is a real life problem, you have to handle that. I will describe that part. This angle is the rotation about earth. I can find out how much roll rate is happening, roll rate with respect to earth, phi dot, okay. How much theta dot is happening here, but theta dot is about the y prime axis, yeah, already tilted. Phi dot is about x EA, theta dot is about y prime. So, when I want to get the angular velocity vector, what I will do is, I use the same equation, I will put phi dot here, okay, and then get this, what is the body fixed, what is the phi dot. But then when I come here, I throw this off, I will put here theta dot, okay, y prime axis, and then I will calculate what is the effect of that. You follow? Because you see y prime is nothing but y body, right. So, basically theta dot becomes basically pitch rate, whereas the phi dot is not exactly the roll rate experienced by the gyro on the vehicle. That depends on what is the orientation of the aircraft at that instant. Okay, that is why you need to solve, even in the navigation of any, what is that, navigation, satellite navigation, aircraft navigation, everything, you have to follow this, because these angles are not small angles, they can be large angle. So, you solve the angle, you get the attitude, you have to solve for that. Now, let us take as it is this one, and we will write our, so I thought I will show directly, yeah, you can do, there is nothing wrong. See, that is where, what is the sequence I should follow, there is some convention, okay, that is it. Then you can follow another sequence, absolutely no problem, but so long as whatever sequence you follow, the results will correspond to that. Only thing is, you cannot compare that number with the result which is following another sequence. Numbers may not match, but the orientation will be fine. Okay. That is, you see, this problem cropped up when people were deriving the equation for a rotor blade, whether you use flap lag torsion sequence or lag flap torsion or this or so many, and in the 70s that was a big debate, and finally when we do rotor blade I will explain that part. Okay. Right now we will go into the equation for, so you got the, now let us look at what are the equations which we need to solve. So, I said first is inflow equation in forward flight, uniform inflow I have taken, please understand. This equation is 1. Then I have thrust equation. When I say vertical force, this is along hub. So, this is the thrust, okay. This is T, this is my capital H, this is my, because T H Y, then you have mx, then you have my, and you have mz, okay. All the loads at the hub. You transfer these loads to the CG, okay. And then of course, tail rotor I have used only thrust, and tail rotor is giving only thrust in this y direction, that is all. I have neglected all other loads, okay, which is okay, which is reasonably all right for most of the analysis, unless you want to complicate more. For a good solution, that is enough, okay. That is why you see the drag force D, which is the fuselage drag, that is along this, along the flight path, this is the D, okay. That is why you see this angle, that horizontal angle, this angle is alpha, okay. So, D cosine alpha, D sin alpha, okay. That is why weight is acting here in the earth system. You put weight, put minus W, because this is acting in the negative z direction. So, minus W, you convert it, find out along what is the force along the z body, okay, because this product you can write, product is actually not, this is essentially cosine theta, sin theta, sin phi, minus sin theta, cosine phi, 0 cosine phi, sin phi, and sin theta, minus cosine theta sin phi, and cosine theta cosine phi, x earth, y earth, z, okay. Now, you see weight is acting along minus W, because that is minus z axis, z earth. So, that will be along the body, you will put this, that will become minus W cosine theta cosine phi, theta is minus alpha. So, you will put cosine, that is why here I have put cosine alpha minus theta flight path cosine phi, and D is here, D acts along the velocity direction, okay. And the velocity we took it as though it is in the x z plane, please understand. That is why I said velocity is in the x z plane. Suppose if the velocity you have a side, the drag will not be in x z plane, drag also will give a side force, you follow. So, all those, that is why when you do vectorially you have to do everything properly. Now, you have the vertical force equation. Similarly, horizontal force you have the hub load, because tail rotor you say it is not giving any vertical force. Suppose if the tail rotor is given, sometimes in the design the tail rotor fin may be like this, okay, okay, something. You may give a slight tilt of the tail rotor, It is not perfectly the shaft, this is the tail rotor. Okay. Looking from back, you may have this is the fuselage which is going. You see this is given a small angle, a little. Maybe in this they can also give it in the front direction. This is called cant angle, okay, few degrees. Yeah, they give a little bit, they can do. Why? Now, a component of thrust, you can use it in supporting the weight, a component, that is all. Okay. But usually cant is not arbitrarily you do not do, because not that everybody goes and gives the cant. Okay. The advantage or disadvantage, whatever it may be, the advantage is they say that I can use the tail rotor force, a component in the vertical direction, that is all.
Is there a limit for the cant angle, or I mean for changing the cant angle?
No, you can't change, fixed. Not that helicopter, oh no way, to introduction in the design configuration, that is all, but not all helicopters have, not all helicopters have. No, random means what do you mean by random? Zero. Most of the design they will have zero. Some helicopters have some angle. Okay. And I have to be very honest, I only know okay the effect of this is it will give some component, because you need to have a tail surface always. Okay. If the helicopter has to fly at a slightly higher speed, you need to have a tail surface. Why means if you do not have, you will not get equilibrium. Moment equilibrium you will not be able to achieve, as a result which means you cannot fly the helicopter at that speed. Engine may have power, but pilot cannot fly, it will not be in equilibrium. So, that is why all the fixed surfaces they introduce. Now, you may say why they have to have a vertical fin, because you asked vertical fin. What happens is that vertical fin will not be at the 0 degree, it is slightly given 1 or 2 degrees okay, to the longitudinal line of the helicopter, at high, that is at an angle of attack. Now, what it will do is it will try to relieve the tail rotor load in forward speed a little bit. Okay. That is all, nothing more, because tail operates in a very complex environment. Okay. Industries will have a test rig, they will do some tests, otherwise all simple calculation is you take the thrust whatever we have for the main rotor is much more complex in terms of the pitch angle etc. Tail rotor is more complex in the aerodynamic environment. Okay. And the distance, these are all important. This is mounted, because first of all the vertical fin you need, because if you want to mount the tail at a slightly higher position from the boom, because you may ask why I have to shift it up, that is like a configuration, because the main rotor, the wake, you do not want to go and hit the tail rotor. So, you try to keep this center along this height, rotor hub height. Okay. So, the tail rotor is not affected by the flow from the main rotor. Okay. If it gets affected, you do not know what is going on. You can say, well, I will put it this here, and if you put it whatever you get, you have to take it, because you do not know how they will interact, the wake from the main rotor, the tail rotor rotation. So, best is you put it up. Okay. Even in tandem helicopter, you see the back one will be up, the front one will be a little lower. Okay. This is to avoid, because you do not know honestly. And but some helicopters you may say, oh, it is there, yeah, our model has not that lifted, it is right on that. So, but we take it, that is all. Okay. Now, the horizontal force, you have again the hub load, the drag and the component of the weight, because component of the weight multiplied with this will give a horizontal force, okay, in the body system. So, you use that term. And then side force, you have the Y, you have the tail rotor, and you have again the W in the Y sin phi minus sign, because this is a W term. So, that side force has again the weight. That is why you see the weight comes in all directions in the body fixed system. Then similarly, you do the moment balance, roll moment, pitch moment and yaw moment. Okay. So, you have the roll moment mx from the main rotor, side force into zh, this is the height, side force, and similarly the tail rotor thrust into z height tail rotor, and then you will have main rotor thrust into yh, because this distance, the thrust is this way, that will give a moment. Okay. If the CG is not on the longitudinal line, no, I will send you these things, this is just for explanation. And then you have pitch moment, again rotor hub, and this is due to thrust, and that is due to again side force, the longitudinal force will give, and tail rotor I have taken nothing. Now, you see in the pitch moment, I do not have any horizontal surface. If I put a horizontal surface here, okay, like a small aerodynamic surface, flat plate kept at an angle, that will give a pitching moment. Okay. So, usually big helicopters they have that. If it is a small weight class, they do not have, but sometimes you will find some helicopters have only 1/2 of the tail, not on both sides, it will be having only 1/2. These are all just for equilibrium. And you can have a vertical plate also, like you have horizontal surface, you can have a vertical plate which is inclined at a slight angle, like your vertical fin. Okay. You can have like this. So, they will give a force. Okay. These are all to relieve little bit. And yaw moment, again the main rotor and the side force will give a yaw moment because of this distance, side force, and of course tail rotor will give, and your horizontal force also will give because of this distance, horizontal force will give lateral shift in the CG. So, these are my 7 equations. Of that, inflow is the first equation. Okay. So, 6 load equation, you may call it equilibrium. Now, how do we really solve? Okay, that is the question. You have to, because where is the flap equation coming in between? Okay. Because flap equation is sitting somewhere, because all these thrust H, Y, Mx, My, they all are dependent on flap response. Okay. Now, flap response we approximated it as though first harmonic, beta naught, beta 1c, beta 1s, that is all, rest of them we neglected. So, all these expressions require flap. So, you have to now introduce the flap equation in between. That is why now you see your equilibrium, this part we will come to that later. This aeroelastic problem is part of trim problem, because you cannot decouple aeroelastic problem in helicopters. Aeroelastic problem is response of the blade to air loads, that will be sitting in between, okay, because you cannot just like that solve equilibrium equation separately, okay, because you must know blade response. Then blade response depends on what type of model you are having for the blade. Okay. Here we have included only flap, please understand, in real helicopter you have to have flap, lag, torsion, all must be included, okay, and it will be much more complex. I will show those results a little bit later. Now, how do you start? Because it is an iterative procedure, you do not know inflow. So, first is you assume my thrust is equal to weight, and always start this analysis from hover case. Do not straight away go and then start solving, okay, I want at mu 0.3, straight away go and then start means sometimes it will not converge. Okay. So, you start from hover, which is the simplest case, you take that equilibrium quantities and then slightly change those quantities, then go to next forward speed, which is 0.05 mu. Because you have to assume, first assumption is assume alpha. Alpha is theta FB may be there, flight path may be 0, may not be 0, that is a given quantity, please understand. Given quantity flight path is there, I may have flight path 0, that means the FP is 0 means alpha I do not know. So, I assume alpha. You may say I assume 0, no problem, because hover I may take it 0. That is why first case hover, whatever result you get in the alpha, if it is 0, when you go to first forward flight of 0.05 mu, you assume 0. Then thrust is equal to totally weight, just approximately thrust is weight. Then you solve for lambda, inflow, because inflow equation I showed you that requires only Ct and alpha. Mu you will know, there is no problem, mu is given, that is the flight condition. So, you first iterate within this, get a lambda, that means what you have done, very first step you got the inflow. Okay. After knowing the inflow, then you go to, so that is why I said use equation 1, that is solve for lambda. Once you get lambda, I have given you in your class notes the flap frequency not equal to 1, equal to 1, I have both beta naught, beta 1c, beta 1s. Solve for beta naught, beta 1c, beta 1s, assuming theta naught, theta 1c, theta 1s. Please understand, you have to assume something. Now, how do we assume? This is from previous flight condition. That is why you take the hover case, first solve for that, because hover is easy to converge. Assume these values, then substitute here, because here this requires lambda, please understand, lambda and theta twist everything. You will get beta naught, beta 1c, beta 1s, right. Now, I have lambda, I have all these quantities. Then go to the 6 equilibrium equations. Okay. What you do is, what are the unknowns for that case? You say I know lambda, beta naught, beta 1c, beta 1s, but I do not know the 6 quantities of theta naught, 1c, 1s, alpha, phi and tail rotor. Tail rotor you can take it as a tail rotor thrust itself. Later you can, once the thrust gets converged, you can actually go and use the simplified form to get the tail rotor pitch angle. Now, when you solve these 6 equations, 6 unknown, they are all algebraic equations. Please understand, they are all algebraic equations, but non-linear, it may be. But after getting theta naught, theta 1 is theta 1s and alpha and phi, you again go back to step 1, because now you know alpha. Okay. You go back, you can again, and you may get the thrust also from the problem, you can calculate, because all these angles are known, you can get what is the thrust. Know the alpha, know the thrust, again get a new lambda. Once you get the new lambda, again go here, solve, and this whole procedure you iterate till equations are convergent. Now, the convergence itself is a very interesting thing. You converge here, then whatever you come here you take it. Okay. But the key problem which is faced is, you will find a thrust which is a dimensional, it is like 4000 kg helicopter or 5000, that is a very big number. Whereas the side force, they are all very small numbers. Then when you try to take equations, you will find that the big number will drive the result, but it may not converge properly. So, always all of them are non-dimensionalized such that they converge, they are all given equal importance, and then you get the converged solution. And once you converge in the pitch angles, then you say your result is over. But you will never get everything equal to 0 beautifully. Some small number, that is okay. If it is 4000 kg, if it comes to 950, all right, 980, because otherwise it will keep on oscillating, the result will keep on shunting. Okay. And these iterations, if you go real complicated thing, it takes about, the problem which we solved, it takes 14 hours for one flight condition, okay, because that is much more complicated, much more complicated. This you can do, because you have everything in the closed form solution, you can write a code. That is why I am saying you can write, I have given every expression to you in the class derived. This can be actually a exercise for the student to see how to solve the problem. Now you see all these equations are there, you write a program, it will not work initially, it will give you garbage. Then you have to find out what error, because even the solution technique has to be proper, it is all algebraic equation. Now I am just extrapolating the complexity, we made several assumptions. One is in the inflow, uniform inflow, it is not uniform, it is variable. The second one is flap, who told you only first harmonic, I should have all the harmonics, then I should have lead lag motion, I should have torsion motion. That means your problem gets complicated, okay, and you should have stall, you have reverse flow effects. When you start adding everything, the problem becomes sometimes intractable, okay. It is a complicated problem. So, what industry was doing? Initially they do lot of approximation, get a result first, after that they will go. That is why here when I use flap, so if you take only flap, you call it flap term. And another thing is, some of the research work, they do not take all the 6 equations, because I do not know tail rotor, I am not interested. So they will say, in most of the research publications, when they are analyzing the aeroelastic response of rotor blade, only blade, then they will take side force equation and yaw moment equation, they neglect it, okay. That means you have thrown away 2 equations. That means what are the 2 unknowns you will throw? You basically throw roll, angle you throw from that, and the tail rotor is thrown. That means 2 unknowns are thrown, remaining is theta naught, theta 1c, theta 1s, and alpha, that is all. But that is for a research publication where you want to study more about only blade response, blade characteristic, influence of certain geometry on the aeroelastic thing. They do not do full analysis of the helicopter. Okay. Now, another aspect is you can do wind tunnel. In a wind tunnel, what happens is it is kept at a specific shaft angle. That means alpha is fixed. That is called a wind tunnel trim. Okay. There you do not go and balance the thrust, because it is held. Whatever force that comes, it is not that it is equal to weight. So, thrust equation is out. You may directly solve, okay, what are the developed force developed only you can say. There is no equilibrium equation. Wind tunnel, what people do is they give prescribed collective, prescribed cyclic, prescribed theta naught 1c 1s. Now, find the response of the blade. But for that you need to know inflow, so they will give the shaft angle, that is all. But you do not know thrust, you follow. So, you have to get the thrust and then get the inflow and then get the all the response quantities. So, depending on the situation, you use that particular set of equations and solve them. Okay. I hope you have, I have conveyed the message here. Now, let us look at some of the how, see, once you have converged, you go back and calculate power. What is the power required for this? Because power equation, you know it, earlier we have derived in the class. Now, I am going to show few results which I have taken from the book and some which we have generated. Okay. You see, in general what happens is beta naught does not vary so much with respect to forward speed. It does not vary a lot up to some 0.3, some mu 0.3, 0.35. It is a very small variation, because the thrust vector is almost supporting the weight of the helicopter. So, it does only with change in weight it may change. Okay. Whereas beta 1s and 1c, 1s I have shown here like this, but actually this is not the, this is some theoretical calculation. Okay. 1c they increase, this also increase with, but this is not correct. This was a main point of research, even 80s later I will show some other results. Some of the experiments show that at low value of mu, the lateral flap, it is about what 2 degrees, 3 degrees, that is all. It goes up and then it decreases. Okay. These are all various theories. This line I wanted to say, this line is my uniform inflow theory. This is the line. Okay. Now, I will come to our results, which we have, this was we published just last year it came, I think last year, yeah, 2009, yeah, 2009. Okay, here is the, we have, this is a complicated problem we have solved. Same thing, flap lag torsion completely, but full 6 degree of freedom helicopter analysis. Okay, this is where it took about 14 hours I was telling you, with the various aerodynamic models. So, if you look at the collective it will decrease and then it will increase. Okay. But you see, as you go to a high speed, that is around 0.35 mu, you see the slope of this curve, it is very steep, the program will not converge so easily. That means, even if the vehicle has a power, enough power, but the helicopter cannot be converged, in the sense trimmed properly, because of it requires very large, it is not restricted. Now, how do you, why this curve shoots up like this? That is because of the fuselage drag. If you reduce the drag of the fuselage, but how do you reduce it? That is the problem. Now, that is why that F which I showed you, equivalent flat plate area for the helicopter, that has to be, if it is brought down somehow, then the curve may tilt, you can go further. If it is there, you just cannot trim, the drag will shoot very high. That is one of the key things. And of course, you see theta 1 S, that is the longitudinal cyclic, you see this is a negative, okay, and that keeps increasing. These are with the different aerodynamic models. Now, here is the theta 1 C, which is the lateral cyclic. With the different aerodynamic models, I am getting different curves. This is the uniform inflow curve, the lowest, the continuous line, and these are, I have included some dynamic stall model and dynamic wake, some additional more complex models. You see they change drastically, okay, just in equilibrium. This was a point of debate. Why the helicopter? It is like this. Pilot wants to fly forward. Usually the general tendency is what? If you want to go high speed, you give more angle. But here, initially you give more angle, then as you increase the speed, you start decreasing the angle. So, from hover you go to very large and then you start coming down. This is, it defies the traditional convention. You want to go high speed, what you do? You increase the throttle. It is not that you go to high throttle for low speed and then come to low throttle for high speed. It does not happen that way. But here this was why it happens. This was a question. A lot of people, of course, it is due to inflow modeling. But inflow and stall put together it came, whereas Dries model which I mentioned to you, that gives slightly this result, but we need to have stall also. And of course, the tail rotor follows similar trend as a main rotor, okay. And these are roll and pitch, but roll attitude we cannot, I do not have data to compare with the experiment, because I do not have data for this with a real helicopter. So, anyway HAL, once we develop, they will be using this code for them, because this is, you can't measure it unless you have some other mechanism. What is the rotor tilt angle, you should measure it and then plot, because the tilt angle depends on where you put your tail, what happens, etc. So, and this is the pitch attitude. So, you see the angle values, that is what I am telling you, approximately it is about 10 degrees, it comes to 7, goes up. Cyclic, that is theta 1s, which is directly related to beta 1c, okay. They go up to minus 10, minus 20. So, the pitch angle can go very high values in the retreating blade, okay. Now, I just want to show this result, because this is what, this also we presented it in the, this is published in the journal. You see, this is the taken from a book, this is the flight test, this is the code which they have used, this is the paper is the Patfield book. I actually took permission from him to put it in my publication, in our publication I would say, because the Lakshman student did. I took his permission so that I can reproduce this in our journal paper, just to say, because I do not have practical data, because usually even if you have one practical data and then show, the quality of the paper will go drastically very high. So, I just wanted to show to the people, look here, this is what the experiment or flight test, qualitative, this is how my data for the given helicopter does. So, different models if I use, see this line looks somewhat like this, okay. This is only lateral cyclic, please understand, rest of them I do not have any data. and this is, you see it goes up to 3 point something, here also it shoots up. That means the rise, steep rise in the angle for trimming. This is only trim problem, please understand. We have not gone to stability, other things. This itself has, then we said this is what, that is why we put qualitative comparison of variation of lateral pitch angle with forward speed. So, this is a present study, this is reproduced from some reference, that is the Patfield book. What I am saying is this we just published last year, AHS, that is Helicopter Society Journal. Okay. Huh? This is a flight test. This is a flight test, but flight test for some helicopter. Please, but this, why I took it is, we all know, everybody knows, this is what happens, okay, in flight. But how do you get that? What model affects your trim result? Simple. So, ours is purely a theoretical study, but we gave various aerodynamic models just to see, hey, if you change this model to another model, what happens to the trim? You follow? And this is only a qualitative comparison. Now, if we want quantitative, then we should take HAL, that is all. HAL should supply the data. See, they also know that now there is a collaboration to make it our own Indian developed code for the analysis of helicopter thing, because please understand, these things take 15 years, it is not one day's job, and a lot of companies they are also working. In US they have put a lot of millions of dollars for developing analysis code. Today they are doing maneuver, we are now doing maneuver for the next thesis, after this is the maneuver. Okay. Now, I will just show you one diagram, it is an interesting, okay, maybe I will show this first. This is what I took it from the paper. See, these are all experimental data. This is the one which I took, because other things are all, everybody gets the trend, there is nothing special, only this is the key. Okay. I just want to show how the angle, pitch angle varies. I have put the numbers here. This is 0.0505, these are nothing but the midpoint of the rotor, and these small numbers 2, 3, 4, 4.55, 5.56, these are effective angle of attack on the rotor disc at various radial locations, because this we took it as 0.23 as the hub, for an advanced speed of 0.01, very low speed. Everything is within the stall angle, that is 6 degrees is the maximum near somewhere near the tip. But when you go to a high speed this is 0.35. You see here these angles are 16 degrees, 15 degrees, that means the blade is start stalling here, and on the advancing side they are about 1.2, here 3, 4, 5, here there is no stall, all the stall goes here, and this is the reverse flow region, very high angle, you can even have, I think we have put minus 180 degrees. Okay. That means the aerodynamic data we have for the full 360 degree rotor airfoil. So, we took the data from a textbook only. Now, that is why at high speed you start stalling on the other side, and that will give you we did vibratory loads, etc. This is just for you to know that how do you do trim problem, but trim problem will give you the vibration load as a part of the solution. That is why you do not solve trim separately, aeroelastic load separately. You have to get both of them simultaneously. But simultaneously means that one shot you will not be able to solve iteration. Okay.